Hi everyone and welcome back. In this video we're going to look at the standard error. So remember back in chapter 3 we found the sample summary statistic, the sample standard deviation, which we calculated first by finding the mean of the sample, which is y bar, and then we subtracted each value with the mean. And that difference gave us the deviations, which some of them were negative, so we end up squaring them to make them positive. And then at the end, we had to take the square root to kind of undo that. So similarly, we can't use the average of the residuals as the typical size because some of them will be negative, right? As we saw, we can get negative residuals when you have a smaller actual value and subtract a larger predicted value. So we have to tweak the formula for the sample standard deviation and make the following changes. Instead of averaging, let me change my color here. Instead of averaging the square deviations from y bar, we're going to average the square deviations from y hat. And then instead of dividing by n minus 1 to average the values, we're actually going to divide by n minus 2. And you might wonder, like, why 2? And it's because we're estimating with, both a slope and an intercept, so two unknowns. Now we obtain the following formula for the typical residual size, and we more commonly refer to that as the standard error. Since we're dealing with residual, remember residual is E for error. So if I look at my formula, we know that y minus y hat is actual minus predicted, which is actually the residual, or E. So really what we have here is the standard error, S sub E, is the sum of all the squared residuals divided by the sample size minus 2, and then take the square root of that. And the standard error just summarizes the typical residual or error size, just like the standard deviation. Remember, the standard deviation was a numbers distance on average from the mean. So this is a numbers distance basically on average from the actual y value. If you're looking at a computer output from a statistical software package, which sometimes my math lab will incorporate into the problems, the standard error is sometimes labeled as RMSE, which stands for the root mean square error. You may also see that in like Microsoft Excel if you have it do some statistical analysis. So let me give you an example of like how would we interpret the standard error. So in the roller coaster example that we looked at earlier, the standard error is about 5.2 miles per hour, okay? We would interpret this as when a model is used to estimate, pardon me, a coaster's top speed based on its height. The estimates will typically off by about 5.2 miles per hour. Okay, give me 2 seconds so I can get a drink of water and clear my throat here. All right, I apologize, thanks. There's two additional things that are often worth looking at when it comes to residuals, besides the standard error. We always want to look at a residual plot, which remember we want to look for random scatter, there shouldn't be any shape to it, and then confirm that the residuals don't have a tendency to grow and shrink in size as you go from low x values to high ones. Okay, there shouldn't be any pattern at all. And then we want to look at the distribution of residuals. If it's consistent with a normal distribution, then it's reasonable to apply the 68, 95, 99.7 rule, which remember we also refer to that as the empirical rule. To the right is the histogram of residuals for the roller coasters. How would you describe the shape of the histogram and what does it imply? So notice we have the residuals here on the horizontal axis and then the number of roller coasters. So if I was looking at the shape, I would say that it's pretty unimodal and symmetric. Okay, so that means it's in line with the normal model. And the distribution of residuals can be reasonably approximated with a normal model. Drawing conclusions about a population based on information in a sample is called inference. Different random samples of data can lead to regression lines that aren't all the same. For example, bridges are professionally inspected from time to time and are given safety scores ranging from 1, which is horrible, to 7, which is excellent. Suppose you want to estimate the average rate at which these safety scores decline with age. Since the cost of inspecting every bridge in a certain region would be prohibitive, you select a random sample of bridges. Below are 2 random samples of 20 bridges from the same population. Okay, what do you notice? Well, they're both scatter plots because we've got 2 quantitative variables. They're very similar to each other, but they definitely have different regression lines. Now look at a simulation of 5 more random samples of 20 bridges. Different samples, as you can see, lead to different regression lines. But luckily, they're not all that much different. However, their steepness or their slopes will be, right? However, the good news is that the lines in the above picture aren't all over the map. They vary a little from sample to sample, but not much. There's different ways of assessing how well a linear model fits the data. The most important is to make a picture. Okay, and we know that graphical displays are important, especially choosing the correct one. Then there are ways of quantifying the fit with a number. Okay, and that number is the correlation, which we talked about in chapter 6. It's the letter R, and that's one such number. Okay, recall that correlation must be in the interval from -1 to 1. Correlation will never be less than -1 or more than 1. Correlation's closest to -1 and 1 mean it's a perfect linear fit. There's a very strong association between the 2 quantitative variables. Correlation closest to 0 means there's no association. So the closer it is to 0, that just means the more the data vary around the regression line. And the closer to -1 or 1, the less they vary around the line. A different way to quantify the fit with a number is to determine what fraction of the variability in the response variable, remember the response variable is y, can be explained by the regression model. For example, a fraction of 0% would mean the model explained no variability in y at all and was useless. On the other hand, a fraction of 100% would mean the linear regression model on x predicted all the y values perfectly. So all the variability in y could be explained by the regression model. So you would want this value to be closest to 100% as possible. And it also depends on what course you're in or what field you're in. In general, when the least squares regression line model is used to fit bivariate data, remember that's 2 variables, the fraction of the variability in the response variable, remember the response variable is the y variable, that can be explained by the model is denoted r squared. Okay, and r squared is just equal to the variability of y hat divided by the variability of y. Okay, or variance of y hat divided by variance of y. Our regression model that predicts maximum wind speed in hurricanes based on the storm's central pressure has a correlation of R equals negative 0.898. We looked at that in a previous video. So what is R squared, and what does that say about a regression model? So R is actually related to R squared. If I know R is equal to negative 0.898 and I want R squared, I'm just going to square both sides. And that's going to give me my R squared value. And when I square negative 0.898, I get 0.8064, which is about 81%. So what that means is 81% of the variation in maximum wind speed, which is my y, can be explained by or accounted for by the hurricane's central pressure, which was X. Okay, some other factors could be temperature, when the storm is over land or sea, etc. But that's a high R squared value, 81%. So we're saying 81% of the variability in the maximum wind speed can be explained by the model for hurricanes and central pressure when that's used to predict. Take a few minutes and pause the video, and you can try the next problem on your own, and then unpause when you're ready to move on. Recall a regression of house price on house size was price hat equals 8,400 plus 88.67 times size. The R squared value is reported as 57.8%, and the standard deviation of the residuals is 53,790. What exactly does the R squared value mean about the relationship between price and size? So differences in the size of houses account for about 57.8% of the variation in the house prices. Remember that we are comparing the X to the Y, and what percentage of Y can be, so Y here, prices, can be explained by X. So 57, another way of looking at it is, the model predicts that about 57.8% of the variation in house prices can be accounted for by the house sizes. So the other prices could be inflation, other factors like the area that the house is located in, etc. Is the correlation of price and size negative or positive, and how do you know? Okay, well, it's going to be positive, and the way I know that is by looking at the linear model. My slope is 88.67, and the slope shows the direction that the line will go in. So I know it's going to be in a positive direction, and the correlation and the slope have the same sign. So positive, and it's because correlation, remember correlations are, and slope, which is B1, have the same sign. you find that your house is worth $50,000 more than the regression model predicts. So in other words, the regression model underestimated the price. You are undoubtedly pleased, but is this actually a surprisingly large residual? So when they say your house is worth $50,000 more than the regression model predicts, they're looking at the standard deviation of the residuals, which is 53,790. That's what that is referring to. Okay, so no, the standard deviation is $53,790, right? And we shouldn't be surprised by any residual smaller than 2 standard deviations. Because anything more than 2 standard deviations away from the average or less than 2 standard deviations away from the average, that would be surprising because it would be unusual, as we learned in chapter 5, right? And $50,000 is less than 1 standard deviation. So we should not be surprised by any residual smaller than 2 standard deviations, and 50,000, right, since that's less than 53,790, 50,000 is less than 1 standard deviation. If we measured the house size in square meters instead, would r squared change? And would the slope of the line change? So the r squared value, remember, is connected to the correlation coefficient, which is not r, which is not affected by units. So r squared would not change. However, the slope would change. The slope does depend on the units. That's the end of this video. We're going to stop here. The last video, we're going to quickly review r squared and kind of finalize what you need to know about that. So stay tuned for one more video. Thanks, everyone.